So we're talking about this process, okay? About how to model our applications and how to implement it inside our database systems. So on the left-hand side, you have your conceptual model that contains conceptually all the data and information that you want to have inside this application. On the other hand, you have your relational model, which actually provide a logical implementation of your conceptual model. And we were talking about this translation process, how to take us input this conceptual model and output a logical schema. And there are a lot of interesting things about this. And there's the baseline process, right? So every single entity site in the ER diagram become a relation, and on every single relationship, right, on the left-hand side, also become a relation. And you need to be especially careful when you're talking about cardinality, when you talk about constraints. But there's another thing that you need to be careful about, which is, given the same conceptual model, there could be multiple ways for you to design the logical schema. So this is one example that we have been looking at for multiple times now. Given the ER diagram in the middle, and we could implement that in different ways. We could have the works in relation, the department relation, stored as a separate relation in a logical schema, or we can just merge them. There are so many different ways you can design this logical schema. And we need to come up with some theory, some principle that really provide us guideline about how to think about these different designs. What the properties do they have, what is a good design, and what is a bad design. And that is what we are going to talk about today. So that goes to the database design theory, right? So the fundamental question is actually what is a good database design, and also how to formally model and enforce the properties that we want in a good design. So there are two fundamental questions, right? The first one is we want to have a precise way to describe the property of our data. And in the last lecture, we talked about a notion of functional dependency as a precise way to describe the redundancy that you have inside your application. And on the other hand, the other side of the coin is actually, given the property of your data, how to describe the property of your database design. And that is something we are going to talk about today by introducing the notion of normal form. But before we talk about normal form, let's just refresh our memory to make sure we both still understand functional dependency, still remember what we know from last lecture, because this is very, very important. So in last lecture, we introduced the notion of functional dependency, and which is actually a very, very simple concept. That is, functional dependency is a relationship between two subsets of attributes of a relation. We see there are two subsets of attributes, A and B, right? So if there's functional dependency from A to B, we say A decide B, right? The semantic of it is, if you think about relation with that functional dependency, it means that you cannot find two tuples that share the same value of A but have a different value of B. That is, in this relation, once I know the value of A, it decides the value of B. Intuitively, that's what it is. So given this relation instance, right, we went through this last time, right? So it's clear to see that functional dependency that A decides B hold in this relation instance, and functional dependency CD decide B also hold, right? And also it's also clear to see that the functional dependency B decides C does not hold, right? If you think about why, is you are able to find two tuples, right, which is the last two tuples actually have the same value of B. They are both have value of B2, but corresponding to different value of C, C3 and C4, right? Because of that, you do not have this functional dependency from B to C. So given a functional dependency, right, alpha to beta, from last lecture, we actually have we actually already know a whole bunch of things about this. So given a relation instance R, and given a functional dependency alpha decide beta, we know how to check whether this functional dependency hold in that relational instance or not. How to check it? Well, you go back to the definition. You pick any two tuples in this relation, and you check whether you can find such a pair that share the same value on alpha but have different beta. Right? It's very simple. We also know that if you give me a collection of functional dependencies, we know how to at least try to derive a new functional dependency alpha decided beta that's going to hold given this collection of functional dependency f. The way to do it is we introduce an inference system that consists of 3 different axioms. And to derive a new functional dependency from a collection of existing functional dependencies, you can just apply these 3 different axioms again, and again. That gives you all possible functional dependencies that can be derived. And this is such 3 simple axioms. There's a reflexivity, right? If you have alpha, that's a subset of beta that implies beta decide alpha, right? So there's the augmentation. If you have alpha decide beta, you can add another attribute gamma on both sides. There is the transitivity, right? When you have alpha decide beta, beta decide gamma, you have alpha decide gamma. The beauty of this inference system is that it's both sound and complete, which means that if you apply this inference rule, derive a new functional dependency, right? It's going. The soundness means that that new functional dependency going to hold. Okay, it's going to be correct, and it's also going to be complete, meaning that all the functional dependencies that hold can be derived in such a way. So this is the fundamental theory behind functional dependency, how to do inference over that. And we also know that given f as a set of functional dependencies, we can also check whether we are able to derive alpha decide beta or not. How to do it? And the way to do it, we introduce the notion of closure, right? You first compute the closure of alpha, which is all the beta that could be decided by this alpha. And we talk about a very simple algorithm about how to do that. If you forget about it, right, go back to the slides of last lecture. There's a very beautiful, simple algorithm there about how to compute the closure of alpha. And you compute the closure, you check whether beta is a subset of that, then you know whether you are able to derive alpha decide beta or not, given this set of functional dependencies. We also know, given a set of functional dependencies, how to compute all possible candidate keys of this relation. How to do that? Well, you go back to the definition of candidate keys. What is candidate key? Right. So if K is a candidate key, you need to satisfy 2 conditions. First one, there need to be a functional dependency that K decide all the attributes. R is all the attributes. And second, such a functional dependency need to be minimal, in the sense that if you remove any attribute in K, that functional dependency will not hold anymore. So a naive implementation of this is you can enumerate all the possible subsets, and for each one of them, you check whether there's a functional dependency from that subset to all the attributes. How to do that? You go to the closure, okay? And then you try to check whether it is minimum. You compete you do this for every single subset of attributes, then you get all the possible candidate keys in your relation. That process now becomes pretty systematic. And we also know how to compute the minimal basis, right? That's a given a set of functional dependency f. Minimal basis of it is another collection of functional dependency that is equivalent to f, but on the other hand, it's also minimal in the sense that you cannot remove any of the functional dependency, you cannot remove any of the attribute on any of the on the left-hand side of any of those rules, like inside G, right, to still make them equivalent. So we talk about all of these things in the last lecture. And today we are going to build on it. So once we understand the notion of functional dependency, we start to have the tool for us to reason about different logical designs. And we start to talk about it towards the end of last lecture. The first application of this is to try to reason about different decomposition strategies of relation. And assuming you have a relation R, and they'll say, okay, so I want to decompose this relation R into two smaller relations, R1 and R2, each one of them holding a subset of attributes, R1 and R2. How can I reason about it? So one property of this is whether this decomposition is lossless or not. That is, if you join this R1, R2 back into a bigger relation, can you recover the original information in R? If that's true, we say this decomposition is lossless, otherwise it's not lossless. So, and we also talk about this condition, right? So as long as there's a functional dependency between, from the intersection of R1, R2 to R1 or to R2, right? One of these hold, then this decomposition is actually lossless. And this is just one example, right? We talked about before. So this is one example that you do not have any of these two functional dependency hold. And as you can see, when you decompose it, when you join the back, you start to have more tuples that's not in the original relation. And this is another example, right? That you do have this hold, right? So the intersection, which is the child attribute, right, has a functional dependency from that to father to mother, right? And because of that, you can actually decompose this bigger relation into two smaller relations. And when you join the back, you get the same thing. So once you know about the functional dependency, you do not need to go through the process to check whether this decomposition is lossless or not. So another property that we could reason about is the preservation of functional dependencies during decomposition. So essentially, you have one relation R, and now you say, okay, I want to decompose it into multiple smaller relations, R1 to Rn. And I have a whole bunch of functional dependencies defined over this big relation. And after decomposition, right, I cannot write down functional dependency across relation. I can only do that for each of these individual relation. Whether the functional dependency, the set of functional dependency for the bigger relation is equivalent to the union of all functional dependencies you define on each of the small relation. If this hold, we say that this decomposition actually preserves all the functional dependencies. So just one example, right? Assuming you have this big relation, right, contains city, contains street, and zip code. And you now decompose it into two smaller relations. The first one contains zip code and street. The second one contains city, content, and zip code. So first one, whether this decomposition is lossless or not, right? So clearly it's lossless, right? If you think about why, is there is a functional dependency from zip code to city and content, right? Once I know the zip code, I know which city of which content it is, right? So because you have this, it satisfies the loss of decomposition condition, right? That is the intersection of these two small relations. Here is the zip code, right? There's functional dependency from that to city and content, right? To one of this. So it's lossless. But whether this decomposition preserves all the functional dependencies, that's actually not true. If you think about why, is in the original relation, we have two functional dependencies. We have zip code decide city and content. We have street, city, content decide zip code. Right? So once you do this decomposition, as you can see, it's very natural to see that you do not have this street, city, content decide zip code anymore, given these two smaller relations. Because all I can define on these two small relations, on the first one, right, there's nothing I can define. There's no functional dependency there, right? So on the right hand side, you have zip code decide city and content. You actually lose one functional dependencies in the big table once you decompose it. So these are the two interesting things about decomposition. Some are lossless, some preserve functional dependencies. So given this, we will start our discussion today about normal form. So what is normal form? There are actually different ways that you can actually organize your logical schema. And if you organize your logical schema that satisfy each of these, like one of this normal form, you immediately know what the property that you have. So what is normal form? The process of database normalization, right? So it's a process that you try to structure a relational database in accordance of sequence of so-called normal forms in order to reduce data redundancy and improve data integrity, right? And normal forms are just common ways that people can do normalization. And for each of these normal forms, we're curious about three different questions. The first question is, if you give me a relational schema R and a set of functional dependencies that you know going to hold for this schema, how to decide this combination, this design R, and this set of functional dependencies satisfy a given normal form. This is about what this normal form is, right? How to decide whether this design satisfies certain normal form or not. And second, if we have a design, okay, R and FD, that satisfies a given normal form, what can we say about this design? What properties are we going to have? And the third question is, if we have a design R and FD that does not satisfy a given normal form, how can we have an alternative design that actually satisfies it? So for every single normal form that we are going to reason about these three different questions. So before we talk about our first normal form, right? So let's try to make sure that we are on the same page that here we talk about a normal form, right? So there's a normal way of normalizing a database, right? So, but being normal doesn't always mean it's good, okay? So something being normal simply means we know immediately how to reason about this property because we saw it before, right? So, and we saw it many times. So in practice, when you actually design a real-world database system, do not be surprised if your solution does not satisfy any of the normal forms, right? So there's nothing wrong about it. So the reason that we talk about these different normal forms is to give you the framework about how to think about data redundancy and how to reason about the property, how to reason about anomalies. Right? It is entirely possible that in real world, when you try to design a real database system, you end up with a design after careful reasoning of all of those, lead to a design that does not satisfy any of these normal forms, and that's entirely possible. But let's try to think about like all those factors when we design this. And let's try to introduce the first normal form, which is called first normal form. So what is first normal form? It's actually a very simple one. It says if your design only contains atomic domains, then satisfy first normal form. So what do we mean by this? By atomic domain, we mean those every single value of every single cell in a relation need to be an atomic value. It's something you cannot tease apart. It can be integer, can be string, can be categorical variables, all those type of things, but it cannot be sets, cannot be array, cannot be list. If you look at the second design, right? So you are saying, okay, so now I want to say, yeah, so this father and mother have multiple children, right? So like in this case, I could have stored them as a set in this cell. It's okay, right? So and the R programming language gave you that capacity. So the first normal form requires you to have the first design, not the second design. That is every single value, you want them to be atomic. If you think about why, the reason that we want first normal form is we want to have the notion of key like easier to be defined. Right? Whenever you have this set value, right? So you cannot think about this like you cannot really define keys in the way that we have been doing so far. But again, like there are a lot of data model give you the capacity to produce a schema that's not in first normal form. And in practice, often the case that might be something you actually want to do. But again, like in this lecture, we assume that first normal form is something that we actually like. So this is a simple one. Has nothing to do with data redundancy. It's just to make sure we have the well-defined notion of keys. Another normal form could be more interesting, and that's called second normal form. And that's actually inspired by data redundancy inside this relation. So let's look at this relation. In this relation, we start to mix two pieces of information together. We have the information about the student, right? So, and we have the information about which lecture that the student actually takes. And the consequence of mixing these two pieces of information together is that you start to have the primary key of this relation as a combination of the student ID and the lecture ID, right? So, and once you have that, you start to cause problems. Before we formally define it, right? So let's just look at different type of data redundancies here, right? And what problem they are trying to they are going to cause. So for every single student, if the student is taking multiple lectures, right, you are going to have the name of the student, the semester of the students being stored actually multiple times. So the consequence of that is you have a whole bunch of anomalies, right? And fundamental reason like that why there's actually a redundancy is you have two functional dependencies in this relation. You have one functional dependency from the student ID and lecture number to the name and semester. This is the primary key, okay? And you have another functional dependency from the student ID to the name and semester of student because that's the student, right? So because you have these two functional dependencies, you start to have data redundancy. Because what does mean by the combination of student ID and the lecture ID to be the key, it actually implies in this relation the student ID could appear multiple times. And because of the second functional dependency, that the student ID actually decide the name and semester. For every single appearance of the same student ID, you are going to have the name and semester being stored multiple times. And this is a very intuitive way to think about why there's even data redundancy, because you have some functional dependency depends on part of a key. And that is the reason why we have data redundancy here. So second normal form try to remove this type of data redundancy. So essentially, given a design, okay, here when we talk about design, it's always about you have a collection of functional dependency, and then you have a logical schema R, okay? So this design is in second normal form if and only if every non-key attribute, every attribute that's not a key, is minimally dependent on every key. Another way to say it, what do we mean by minimal dependent? It means that you do not have any attribute that's not a key that's functionally dependent on part of a key. So that is actually what we mean by that. So, I mean, if you look at our original example, right? So look at this one. So this functional dependency from student ID to name and semester is actually the reason that this design is not in second normal form. Because you take name, which is an attribute that's not a key, a non-key attribute, that actually depends on the student ID, which is part of the key. Because the key of this relation is the combination of student ID and the lecture ID. And because of this functional dependency, this schema, this design is not in second normal form. And also because of this functional dependency, there are data redundancies in this relation. So there could be a whole bunch of problems if your design is not in second normal form, and that is why, at least in practice, at least we want your design to be in, I mean, I cannot imagine a case that we do not want your design to be in second normal form, because there are so many obvious problems if your design is not here. So there could be insert anomaly, right? So you have students who attend no lectures, right? So what should you do, right? You need to put all those null values. You need to remember to put all those null values, right? There could be update anomaly, right? You increase the semester number of one student. You need to do those multiple of those tuples. And there could be delete anomaly, right? So when some student drop all the courses, right? So you need to be really careful to not delete that student from the system, right? So all this can lead to redundant and inconsistent updates of the relation, and actually could hurt your data integrity. So that is why in practice, I would be really surprised if at the end of the day you decide to do something that's not in second normal form. Yeah. So we have one question. Could we say that we have second normal form if every key is a candidate key? I think you mean every attribute is a candidate key, right? So if every attribute is a candidate key, then I think it will be in second normal form. Yeah, that answer your question? Yeah. Any question about this? First normal form, second normal form, any questions? Okay. So how to enforce second normal form? Now we have a design that's not in second normal form. What should we do? One way to enforce second normal form is as follows. You take the evil functional dependency, and it's a functional dependency that makes the design not in second normal form. In this example, it's a functional dependency from student ID to student name and semester. And you can actually decompose this big relation into multiple smaller ones. You can create one smaller relation that contains all the attributes in this evil functional dependency. Here you have a student table with student ID, the name and semester. And then you have all the other attributes plus the key of this first relation into a second one. Your second one have a tense, contains only student ID and lecture ID. So once you have this, right, and then start to make sense, because if you look at the student relation, right, so all the non-key attributes, name and semester, depends on the key, not the part of the key, because the key have only one attribute. And if you look at the second one, the same thing holds. That is, every single of the small relation will be in second normal form once you decompose it. And this decomposition will be lossless. Why? Because in the decomposition process, when you have the first relation, right? So you already have one functional dependency, right? So, and that's actually satisfies the condition of a decomposition being lossless. So this is going to give you a lossy decomposition that every single small relation going to satisfy second normal form. So far, so good. Any questions? No? Okay. So one question I want to think about is, now we know this notion of second normal form, and we know if something is not in second normal form, there could be data redundancy. But does second normal form get rid of all the data redundancies, right? So that's one question that we want to think about. Now let's look at this example. We have this relation R with two functional dependencies. We have AB decides CD, okay? So essentially it simply means AB, these two attributes, is the key. AB decides CD. This one functional dependency. And we have another functional dependency, C decides D, okay? The first one is whether this design is in second normal form. Who thinks this is in second normal form? Who thinks it's not in second normal form? The way to think about it is to look at every single attribute. you look at attribute A, you first think, whether it is a key. It's part of a key. It's AB. AB is a key, right? A is part of a key. Fine. It's not a non-key attribute. Okay. B is also not a non-key attribute because AB is a key. You look at C, it's a non-key attribute. And they'll start to think about whether C depends on part of a key. Essentially, the way to think about it is whether the functional dependency that A decides C or B decides C hold. If any of these hold, then that is the evil functional dependency. In this case, we don't have that, right? B doesn't decide C, A doesn't decide C. And you go to the first one, you go to D. Again, you check whether A decides D or B decides D, whether D depends on part of the key. In this case, it's also not the case, right? C decides D, but A and B doesn't decide D, right? So that is actually the reason that this design is actually in second normal form, because every non-key attribute, which is C and D, they minimally depend on the key, which is A and B. It does not depend on part of a key. Make sense?
But A does decide C, though, because if you have an A, we already know that it has to be a C in C. Like if you have a small A, you can call it A.
Oh, yeah, sorry. Yeah, so when we talk about design, we talk about schema and set of functional dependencies. We don't consider the content of the relation when we talk about design. Yeah, so when we talk about design, is for all the possible things you can fill into that schema, this is a property. Yeah. So like all of these are just one example. Yeah. Okay. So when we talk about design, there's a schema, there's a set of functional dependencies, and nothing else. That's a design. Okay. We don't know what you put inside that. Okay. Any other questions? Do you agree this is in second normal form? Do you agree? Okay. But are there data redundancies? If you look at this, right, so I mean, there are data redundancies. I'm showing you one example content here. That you could have two tuples sharing the same value of C, right? But once you have that, because of functional dependency that C decides D, you end up storing the D for that same C multiple times. That is why if you look at two tuples, there are two copies of C and D being stored in this relation. So clearly there are still data redundancies in this design. And there could be instances that have data redundancy. And once you have that, and all those problems will still be there, right? Because whatever update anomaly or delete anomaly, insert anomaly that you have, if something is not in the second normal form, will still hold for C and D, right? Because whenever you have the same C, you need to store that multiple times. This actually means that our notion of second normal form is not strong enough to get rid of all the data redundancies. So we need something stronger, okay? And that gave us another normal form called third normal form. So we say a design R is in third normal form if and only if the following hold. That is, for all the for each of the functional dependency alpha to beta, for all of those alpha to beta, at least one of the following hold. Either this is a trivial functional dependency, which means the right-hand side is part of the left-hand side. Okay, it's either a trivial one, or the right-hand side is an attribute of at least one key. Or the left-hand side is a super key. It's a superset of some keys. If for all the functional dependency that you have, they satisfy either one of these three different conditions, then we say this design is in third normal form. The intuition behind it is if you have a functional dependency that doesn't satisfy any of these conditions, then that's a very strong indicator that alpha itself is actually a concept of entity in its own right, so should deserve its own table. So that is actually the intuition behind this. So another intuition is, if you think about why we've done these three different things, we are actually trying to get rid of the type of transitive dependency. That is, you have A decided B, and you have B decided C. Once you have these two things in your relation, or like in your design, then you start to have data redundancy. So third normal form try to get rid of that. So, and also you can see the one on the right-hand side, right? The thing that we written that's actually in second normal form, in this case, it's actually not in the third normal form. Why? Because if you look at the functional dependency that C decide D, right, how to think about it, let's check each of these conditions whether it hold or not. First one, C and D is not trivial, right? The right-hand side is not part of the left-hand side, right? So not trivial, doesn't satisfy the first one. And second, if you check the right-hand side, which is D, right? So that's not an attribute of some keys, right? The only keys that you have in this relation is AB, right? The right-hand side of the functional dependency, D, is not part of it. And also, the left-hand side, which is C, is not a super key, right? Because the key is AB, right? C has nothing to do with it. So this is one functional dependency that does not satisfy any of these three conditions. And because of that, this design is not in third normal form. Make sense? Any questions about this? No? Any question online? No? Okay. So as you can see, right? So once we have this third normal form type of notion, right? It tries to get rid of a whole bunch of data redundancies. But is that the end of it? Can you construct a design that's in third normal form but still have data redundancy? So let's look at this example together. Again, we have relation R, but with a different collection of functional dependencies. We have one functional dependency from ABC to D, okay? Which essentially says that ABC is a key. And second functional dependency from D to C. Okay? I have ABC decide D, and D decide C. Okay? Have a look back. First one, whether this one is in third normal form or not. But to think about it, you go through every single functional dependency and try to check whether they satisfy one of these three conditions or not. If you check the second one, from D to C, right, it's not trivial. You check the second condition, whether the right-hand side is at least one key, that's actually hold, right? Your key here is ABC, right? The right-hand side of the second rule, C, is part of the key. It actually satisfies your second condition of your of third normal form, right? So it's fun. So this is actually a schema that's actually in third normal form. But on the other hand, do we have this redundancy in this one? Again, we do, right? If you look at the column C and D, because of the functional dependency that D decides C, for the same value of D, which could appear in this relation, you are storing multiple same copy of C, right? And this is just one example of the schema that have that type of data redundancy. Again, once you have that, you still have a whole bunch of update anomalies and delete anomalies for this. And fundamental problem of why it still have this redundancy is you still allowing this functional dependency D to C in third normal form. If you want to get rid of all those data redundancies, we need to define something even stronger than third normal form. And that's to give you another one called Bcnf. So this is a definition. We say a design is in Bcnf if the following hold, if and only if the following hold. That is, for all functional dependency F to be in this design, so like in your application, at least one of the following two conditions hold. Okay? Either this is a trivial functional dependency, or A is a super key of R. So as you can see, we get rid of the second condition in the third normal form. We have an even stronger type of normal form, which, if you look at this, pretty much says you cannot have any of the functional dependencies that are not trivial at all. If something Bcnf, it means that for all the functional dependencies you have in this application, either it's trivial or the left-hand side is super key. Pretty much says you cannot have any non-trivial functional dependencies in this design. As you can see, it's much stronger than third normal form. And the intuition behind it is to get rid of all those data redundancy caused by functional dependency. Let's try to make sure that all the functional dependency I have is somehow trivial. Okay? So that is the intuition behind it. Now let's look at this example, right, and try to decide whether it's in Bcnf or not, or whether it's in third normal form or not. So it's the same thing, right? You have ABC decide D, you have AD decide BC. In this case, you have two candidate keys. You have ABC, which is a key. You have AD, could be a key. And then you have the functional dependency D decides C. In this case, it's actually in third normal form, right? Why? Because you check the D to C, in this case, right? The right-hand side C is part of a key, so it's in third normal form, but it's not in Bcnf, okay? So if you look at why, it's because of the D decides C. If you look at this, it's not trivial, and D is not a super key. So because of that, this design is actually not in Bcnf, okay? So now we have this different notion of normal forms. We have first normal form, we have second normal form, we have third normal form, we have Bcnf. There's 4 different things. The moment you get stronger, okay, from first to Bcnf, that direction, you get stronger. You start to eliminate more and more data redundancies caused by functional dependency, okay? So that is what we are trying to do. And now we have this. Remember the 3 questions we want to reason about for normal forms. We know the definition. We know how to check whether design is in each of these normal form or not. So there are still multiple questions left that we need to understand. The first one is, assuming I give you a database design that's not in Bcnf, how to turn that into something that's in Bcnf. And second question is same for the third normal form. If I give you something that's not in third normal form, how can you turn your design into third normal form? And third question is, why do we need third normal form when we already have Bcnf? Why do we even need to introduce the whole bunch of those normal forms? Why don't we just start from Bcnf to say, whatever design you have, you cannot have all those non-trivial functional dependencies. Why don't we just have that? Because it eliminates all the data redundancies. Why do we even need third normal form when we have Bcnf? So as you can see, as you will see in the second half of the lecture, there is actually a very interesting trade-off between correctness and efficiency. Okay? Getting rid of data redundancy is not always good. Sometimes your Bcnf is way too strong. It's prioritized too much in getting rid of data redundancy, but forget about enforcing kind of functional dependencies, right? like enforcing correctness. So you're going to see what I mean by that, right? So there are still these 3 questions left, right? So now let's take a break. When we get back, we talk about these 3 questions. Okay, so let's continue. Yeah. So we have 3 questions that we need to understand. How to turn database schema into Bcnf if it's not in Bcnf. How to turn a database schema into third normal form is not in third normal form. And what are the relationship between third normal form and the Bcnf, and why do we need both? So now let's look at the first question. And that is, if I have a database schema R that's not in third normal form, how can I decompose it into a whole bunch of smaller relations, R1 to Rn, such that satisfy two conditions. The first one is this decomposition need to be lossless. I do not want to lose information, right? If you join R1 to R1 back, you can recover information perfectly in the original relation. And second condition is for each of these smaller relations, R1 to Rn, they are in Bcnf. Okay? So this is the algorithm that we want to understand. So it turns out there's a very simple way to do it. And it works like this. You start from this big relation, and you check whether it's Bcnf or not. If it's already in Bcnf, then you return. Then you are done, right? You don't need to do anything. If it is not in Bcnf, essentially you are able to find one evil functional dependency. Right? That's why it's not in Bcnf. You are able to find an evil one from alpha to beta that make this relation not in Bcnf. And then what you are going to do is you are going to create two smaller relations. The first one contains both the left-hand side and right-hand side. You have alpha union beta in one of the smaller relation, and then in the other relation, you take the original one, right? You get rid of beta. You get rid of the right-hand side. And then you put these two relations into your result side. You continue to do this until all the relations in the result side is in Bcnf. And then you are done. Okay? So it's very simple. The way to look at this, if you look at this relation, you first check whether it's in Bcnf or not. I mean, in this case, not, because you have one functional dependency that D decides C that causes a problem. And then what you're going to do is, okay, now let's decompose it. I decompose that one relation contains both C and D, this one relation. And then I have another relation without the attribute C, then get something like this. Okay? This is one step of decomposition triggered by this evil functional dependency. And then what we are going to do is to take these two relations and you check whether they are in Bcnf or not. Right? In this case, they already are, then you return. Okay? So this is a very simple algorithm. The way to think about it is once you have this functional dependency from alpha to B, for example, right? You try to decompose it. You have one relation containing only the left-hand side, and then you have the original relation without the right-hand side. So that's the decomposition algorithm. Now let's try to reason about the property of this algorithm. The first thing that we can say is all of those smaller relations, R1 to Rn, they are in Bcnf when you return. Right? That's clear, right? Because otherwise I won't return, right? That's almost by definition. And the second statement that we can make about this algorithm is R1 to Rn is the lossless decomposition of R. So how to prove that? And the way to prove it is by doing induction. To say, yeah, you want to prove every single time you decompose, you have a lossless decomposition, right? So in this case, right, your decomposition actually satisfies the lossless decomposition kind of condition that we have, right? Because the only reason you are decomposing it is because you have a functional dependency from alpha to beta, right? If you take the intersection of the two small relations, you get alpha, right? And then you have one relation containing alpha and beta, and there's a functional dependency from alpha to beta. So every single of the small decomposition is lossless, and then you do the induction, okay? So essentially, once you return, you have a lossless decomposition of your original relation. So third statement that we can make is this one going to terminate. This algorithm will always finish running. It won't stuck forever. The way to prove it is by the counting of functional dependency that you have. You start from a finite amount of functional dependencies. Every single time I decompose it, I get rid of one functional dependency. Okay? So in the, so that functional dependency won't be evil anymore, right? So you have those candidate evil functional dependencies start from a finite number. Once you decompose it, you get rid of one, right? So this algorithm is going to terminate in finite amount of steps because in the input, you have finite number of functional dependencies. And whenever I decompose, I monotonically decrease a finite set. So this is just informally, right? So why this works, okay? It's going to give you a R1 to Rn that each one of them is in Bcnf. Them together give you a lossless decomposition, and this algorithm will always terminate in a finite amount of time. Now let's look at one example and think about how that algorithm going to perform in this example. Now I have this huge relation contains a whole bunch of different pieces of information mixing together. So I have the professor number, the name, the level, the room, right? The city, street, zip code, area code, content, and population of the content for whatever reason. I put them all into the one big relation. Okay? So as you can see, there's a whole bunch of functional dependencies here, right? So the key of this relation is the personnel number of the professor. Once you know the personnel number, it decides pretty much everything else. Okay? And then another functional dependency is if you know the room of professor, you know which professor it is, right? Room decide personnel number, street content city decide zip code, city content decide population area code, zip code decide content city. So this is the collection of functional dependencies that you have. So if you run the algorithm, right? So the first thing that to check is you try to find candidate keys. Okay. So the way to do it is you generate the closure, and then you try to find all the keys, right? In this relation. In this case, personnel number is a candidate key. And also the room is a candidate key. Because once you know the room, you know the professor. Once you know the professor, you know everything else, right? So there are actually two candidate keys in this relation. Either the personnel number or the room. How to decide it? You compute the closure of personnel number. You will see the closure of personnel number is going to be the whole set of attributes. The same for room. And then you check each of these functional dependency and see whether this relation is in Bcnf or not. Okay? So in this case, right, so clearly it's not. So there are so many different functional dependencies that violate our condition. But you can pick one of them. Okay? For example, you can say, yeah, zip code from decide content city in this case is clearly an evil functional dependency that makes the relation not in Bcnf. So take that, and then you decompose. Okay? In this case, how to decompose it? You can create a new relation, right? Contains all the attributes in this evil functional dependency. Zip code, content, city become a new relation called zip code, for example. And then you have the other, and you take the original relation and get rid of the right-hand side of the functional dependency, right? You could have another one, for example, professor new, without content city there. And then what I'm going to do next is to repeat these three steps on each of these new relations and continue. Right? So in this case, to look at this new relation, without content city here, right? You have a whole bunch of functional dependencies that hold on this relation. Okay? So, and then you continue, right? So what is the key of this relation, right? So again, professor name, like personnel number and the room is still the candidate key of this relation. And you say, yeah, so let's check each of the functional dependencies to see whether this new one, right, is in Bcnf or not. In this case, right, so you say, yeah, I mean, there's actually another evil functional dependency that zip code decide population and area code. Right? And then you do decomposition again. Then you have two new relations. One contains the zip code and area code and population. Another does not contain information about area code and population. And you continue. You continue this for each of these new relations until all of the relations you have are in Bcnf. So in this case, right, so decomposition will look like this. If you look at each one of the smaller relations, they are already in Bcnf. And it's clear to see that they actually form a lossless decomposition of the original relation. You can recover the original relation by just join join everything on zip code. Okay? So that's what you have. Make sense? Any questions so far about this? Questions? Question online? No? Okay. So one thing that's getting interesting is if you look at this decomposition, that this preserve all the original functional dependencies. And that's a different question. We know this decomposition is lossless, so we are happy about it. But why does it preserve all the functional dependencies? So what's interesting about this decomposition algorithm for Bcnf is once you decompose relation, you could actually lose some of the functional dependencies. So for example, look at this one. In the original schema, I have one functional dependency that street contains city decide zip code. That's not here anymore. I do not have a table anymore that contains information of street, content, city, and zip code in the same table. And from all the smaller functional dependencies that hold for each of this relation, I cannot prove this functional dependency. So essentially, during decomposition, even though you are not losing information in the sense that you will have a lossless decomposition, you can still recover the original relation. But some of the functional dependencies in the original relation could get lost. Okay? This is just one such example of this algorithm. If you look at this, right, Bcnf decomposition does not preserve all the functional dependencies. It tries to get rid of data redundancy. So that's the game that we are playing. We are getting rid of data redundancy. The price we pay is somehow we could lose some of the functional dependencies in the original thing. And another property that we have is to think about whether it's getting rid of all the data dependencies, all the data redundancies. So in this case, so Bcnf essentially get rid of all the data redundancy that's introduced by functional dependency. So it's only one type of data redundancy. It doesn't get rid of all the data redundancy. Okay? It just gets rid of all the data redundancy caused by functional dependency. So later we are going to see another type of dependency between attributes that even Bcnf doesn't get rid of the data redundancy for that part. So this is the property of Bcnf decomposition. Another thing is that if you think about the algorithm, the way we proceed is to take one evil functional dependency, right? But there could be multiple of those, right? Depending on which one that you pick, you could have different decompositions, right? In the previous example, right? So we pick, I forgot which one we picked first. We pick zip code, decide content city, and decompose it. That's why we have this small relation zip code, content city. But you could pick another one to start with. You could pick, for example, street, content city, decide zip code if you really do not want to lose it, right? So, and then you will have a different strategy. You have different decomposition strategy. Then you will have another relation contains zip code, street, content city, right? So you have a different thing. So how can we decide which functional dependency to start with? So that's actually a kind of pretty delicate question. There are multiple factors coming into that. First one is, one thing that we can see is whatever functional dependency that you are picking to do the decomposition with, that functional dependency will not be lost, right? So because there will be one table holding that, at least for that step, that thing is not lost. So essentially, if you have a functional dependency that you really do not want to lose, right? So try to prioritize decomposition with that. If you do not have such a preference, one heuristic that people often do is you pick actually the functional dependency with the largest right-hand side, right? To really decompose, to really kind of balance out the decomposition, because like essentially like the way to do it, right? So once you do decomposition in the original relation, you are going to get rid of the right-hand side. Okay. One heuristic that people often do is heuristic, which means there could be corner case that doesn't really make too much sense, but often it makes sense, is to prioritize those functional dependency that have the largest kind of right-hand side. So this is about Bcnf and how to decompose a relational schema that's not in Bcnf into Bcnf. And once you do that, you get rid of data redundancy caused by functional dependency, because all the functional dependency here now is kind of trivial now. And second, you could lose some of the functional dependency in the original relation. Any questions about this before we move on to another algorithm? Questions? No? Okay. Now let's talk about third normal form. Okay? It's slightly weaker than Bcnf. So again, what is third normal form, right? We say a design is in third normal form if and only if you take every single of the functional dependency, it's either it's trivial, or the right-hand side is part of a key, and or another condition is the left-hand side is a super key, right? So we add one additional condition, right? So compare with Bcnf. The thing we want is, assuming we have a schema R that's not in third normal form, right? How can we actually output R1 to Rn such that R1 to Rn is a lossy decomposition of R, and every single of this relation, R1 to Rn, is in third normal form. That's what we want. So it turns out the algorithm to do that is actually also pretty simple. And that's the algorithm that we call synthesis algorithm, because it's not decomposition, because it goes the other way around. That's why it's synthesis. So the way to do it is to compute the minimal basis of f. Okay? F is the input functional dependency that you have. You compute the minimal basis. So this is the minimal set of functional dependencies that describe my original set of functional dependencies. You first try to simplify it. You compute the minimal basis. And then for every single functional dependency in the minimal basis, you create a new relation. Assuming you have alpha to beta in the minimal basis, then you create a new relation contains both alpha and beta. And then, if none of these relations that you created contains a super key of the original relation, then you create a new relation with that with a key. Okay? And then you end up with a whole bunch of relations. Some of this relation contains some of this relation is a subset of some other relations. In that case, you merge them. Okay? You merge those relations that one is a superset of the other, and you are done. Okay? It's very simple. You start from a set of functional dependencies. You compute the minimal basis. How to compute the minimal basis? We did that in the last lecture. You have a minimal basis. For every single functional dependency in the minimal basis, you create a new relation. And then you check whether you have a relation that contains the key. If you do not have it, you add a new relation containing the key, and you merge all the relations that subsume each other, like one another. Okay? So now let's look at this example. We have these two functional dependencies, AB to CD and C to D. And it's not in third normal form. And we try to do something about it. The first thing is, okay, let's try to compute the minimal basis. If you compute the minimal basis, right, so it will look like this. You have two functional dependencies. The first one is AB decide C and C decide D. Okay? It's simpler than the original one. You do not have the AB to D anymore because AB to D can be derived from these two things. You have AB to C, C to D, you have the transitivity, right? So you have AB to D derived from the basis. So you first simplify it, okay? You first compute the minimal basis of your input functional dependencies. And then for each of the functional dependencies in the minimal basis, you create a new relation. From AB to C, you create a new relation contains ABC, this, all the attributes. From C to D, you have a new relation contains two attributes, C to D. And then you check whether you have a relation here, these two, whether you have one relation contains a key. In this case, the key of this relation is AB, right? And you have one relation contains AB, so you're happy. You do need to add a new one. Then you check whether one relation is a superset of the other one. In this case, no, so you are happy. Then you are done, okay? So, and then essentially you generate this lossless decomposition. One is ABC, another is CD. That each one of them is in third normal form. But on the other hand, they have they are lossless decomposition of the original one. Okay? It's a very simple algorithm. Now let's look at one concrete example about how to do this. Again, still this example. You have this big relation with a whole bunch of information fused into that. And you have, as input, a collection of functional dependencies. So what should we do? You first generate the basis. You try to simplify this collection of functional dependencies, right? And then you generate relation for each of these functional dependencies. So here we already do the basis for you. This is actually already the basis, okay? So, and then what we are going to do is for every single functional dependency in this basis, you create a new one. The first one is for personnel number to name, level, room, city, street, and content. Then you have a relation look like this. The second one is room to personnel number. You have like this. For every single functional dependency in the basis, you create a new relation. Okay, that's step one. And then you check whether one of this relation contains a key. In this case, right, your key is personnel number and room, right? And there are multiple relation contains those. The first relation contains the personnel number. The second contains the personnel number and the room, right? So it's fun, yeah. So you do have relation contains a key. You're happy. And then you kind of need to merge relations, right? So like in this case, what are we going to merge? If you look at the second relation contains personnel number and the room, it is a subset of the first relation. The first relation also contains personnel number and the room. Then you actually merge them to only keep the big one. And if you look at, for example, I think there's another one. If you look at the last one, right, city, zip code, and canton, right, that is the subset of the second one, city, street, zip code, and canton. Then you merge them, you keep the big one, right? So once you merge, then you are done, okay? So this is actually how to generate a lossless decomposition of the original relation, that each one of the smaller ones is actually in third normal form. So the first thing that we want to understand is whether this is lossless. Yeah. So like whatever thing that you have is going to be lossless. Okay. And second is whether it preserves all the functional dependencies. So this is actually, yes, different from Bcnf. If you do this synthesis algorithm, it's going to preserve all the functional dependencies. Why? What's the reason? If you think about the reason, is for every single functional dependency in the basis, I create one relation to preserve that. Right? So that is, by construction, the algorithm. For every single functional dependency, I create a new algorithm, I create a new relation, and inside that relation, that functional dependency is being preserved. because I do that for the basis, right? So I'm going to preserve all the functional dependencies that allow me to recover all the previous functional dependencies you have in your input. So it's going to preserve dependencies. And third thing is whether it gets rid of all the data redundancies. This is actually no, right? Because it only enforces third normal form, but not Bcnf, right? So it's actually going to still have, could have, some data redundancies caused by functional dependency. And again, in this example, right, you end up has one relation with city, street, zip code, and content, which is actually not in Bcnf, but in third normal form. So if you look at these two things side by side, okay, now we introduce these two different algorithms. One gave you third normal form, another gave you Bcnf. If you look at this side by side, you can see this trade-off. On one hand, if you have third normal form, you try to model all the functional dependencies. You are saying, okay, I want to get rid of data redundancy, but I cannot lose functional dependencies. It's going to preserve all the functional dependency. But on the other hand, the downside of that is you still could have data redundancy caused by functional dependency. When you go to Bcnf, the view is, okay, I do not want data redundancy. I'm going to prioritize getting rid of all the data redundancy caused by functional dependency. And the consequence of that is you could lose some of the functional dependency. If you think about the preservation of functional dependency as correctness, that is all the constraint you have on your data, the third normal form is actually prioritizing correctness. And if you think about data redundancy as efficiency, that's your efficiency of your storage, Bcnf try to prioritize efficiency. So that is why we have these two things. In many of the applications, it's very hard for you to get both, right? So you want to get enough efficiency and enough correctness to make sure you can model your application in a level that's actually enough. But the moment you go to the extreme case, that I only care about correctness or I only care about efficiency, it is often the case that you can only get one, not both. Which one to pick in an application actually depends on in the application which part you actually cares about. If you have application that you really care about efficiency, that data redundancy actually is just causing so many problems, what you are going to do is going to prioritize to Bcnf, and then you try to enforce the functional dependency that get lost at the application layer, not at the design layer. Okay? If you have an application to say, yeah, I really care about correctness, I'm okay with some of the data redundancy, then you are going to have a decomposition or like a design that's in third normal form. And because of this, you are going to have update anomaly, right? So insert anomaly, all those type of things. And then you are going to manage them at application layer. Whenever someone writing a SQL query, you have additional check to see whether they satisfy the condition that get rid of all those anomalies or not. So there need to be something happen at the application layer. Either you check the functional dependency, or you check those data redundancy, those data anomalies. Okay? So you can, there are cases you can get both, but there are also many cases that you cannot. That is why we have these two things. Okay? Make sense? Any questions? I think that we have one question. Okay, well, we have one question. Why are those functional dependencies already a minimal basis? Shouldn't there only be a single attribute per right-hand side? Oh, yeah. So, okay. So, yeah, so that's a very good question. Yeah, so that's a very good question. So, here we talk about all of this in minimal basis. So the reason we talk about it is, yeah, so last lecture when we talk about minimal basis, we say on the right-hand side there's only need to be there can only have essentially one attribute. Yes, this is just a shorthand to make sure we don't have a super long like collection of functional dependencies. Yeah. So the definition of minimal basically doesn't change. This is just a shorter way to write it down. Okay? Yep. Okay. So now we have this third normal form, and now we have Bcnf. Now let's continue this. Is Bcnf enough if we worry about data redundancy? And we talk about Bcnf actually does not get rid of all the data redundancies. It just gets rid of data redundancies caused by functional dependency. So what could be potential problems of Bcnf? Now let's look at this relation. Assuming we have a relation contains these two different pieces of information. We have for each person which language the person speaks. We also have another piece of information, which is for this person, which program language that this person knows how to code in. If you think about this, these two different things are actually independent with each other, right? For example, for this person, 3002, right? So this person speaks two languages, right? Greek and Latin, and also can program in two languages. Because these two factors, at least in this application, is independent from each other. What language you speak has nothing to do with program language you can use. You end up with 4 different roles for this person. Right? 2 languages, 2 program languages, because they're independent. Right? You need to store actually 4 tuples. So clearly there are data redundancies here, right? Because I'm storing multiple times that this person can speak Latin, for example. But let's think about whether Bcnf gets rid of this. What is the highest normal form of this one thing? Right? So this one is actually in Bcnf. If you think about why, it's because what are the functional dependencies that we have here? Do we have person to language? No, we don't have that, right? Because one person can speak multiple languages. Do we have person to programming? No, we also don't have that, right? Do we have language to person? No. Do we have program language to person? No. Essentially, there's no functional dependency here at all, right? The primary key of this relation is these 3 tuples: personnel number, language, and programming language. There's no functional dependency at all. So by definition, it's in Bcnf. So it's actually in Bcnf, but there's still data redundancy. And the implication of this is that we talk about the functional dependency as one way to describe data redundancy. But that doesn't describe all the data redundancies that you could have. So we are lacking another fundamental tool to talk about different type of data redundancies. And that is why we need to go beyond functional dependency. So before we talk about what that type of dependency is, let's try to say, yeah, I mean, if I want to store this piece of information, there's a simple way to do that. Is I could have a schema design that looks like this, right? If you allow me to use those non-atomic values, I could store for every single cell a set of values. Right? Instead of treating language as a value, as an atomic value, I store it as a set. Okay? So this person, 3002, speaks 2 languages, so I store that as 2 values. Right? So as 2 programming language, also 2 values in the set. So I could do that. There's nothing stop you from doing that in practice. And if you have an application that really fall into this, right? So we really recommend you to actually do this. So the problem of this is this one will not be in the first normal form, okay? Because that one will have non-atomic value. Again, there's nothing wrong about it, okay? And in the latest SQL standard, you are able to do it. If you are modeling your data as XML, you are able to do it. There's nothing stop. There's nothing wrong about doing that. So, but what if you really want to stay in the framework of first normal form? So what should you do? So essentially, I'm going to introduce a new notion of dependencies that to really model the following phenomenon, that is, condition on some attribute. In this case, condition on the person. There are two different attributes are independent with each other. The value of some attribute has nothing to do with the value of other attribute, condition on the same person. How to describe that phenomenon? That's actually interesting. And with functional dependency, we cannot really define that. So that get to a different type of dependency called a multivital dependency. So essentially, assuming I have a relation with three different collection of attributes, A, B, and C. Okay? And then we say there is a multivital dependency. You have these two different arrows instead of a single one, like functional dependency, from A to B or A to C, right? To really model the phenomenon that condition on A, the value of B and C are independent with each other. So that is what we are trying to model. So how can we model that? So formally, this is what we do. We say there's a multivital dependency from alpha to beta in a schema with three different collections of attributes, alpha, beta, and gamma, right? Assuming we say, yeah, there's a multivital dependency from alpha to beta, we mean the following. That is, if you take any pair of tuples in this relation, T1 and T2, that they match on alpha, okay? This implies that you can find another pair of tuples, T3 and T4, in the same relation, such that all those four tuples share the same value on alpha. T3 and T1 share beta, T4 and T2 share beta, and T3 and T2 share gamma, and T4 and T1 share gamma. Essentially, it means that how can we model something being independent? It is, if you give me two tuples, T1 and T2 share the same alpha, if I swipe their beta and gamma value, I can find those two tuples in the relation. So their beta and gamma doesn't really matter too much because I can swipe them and generate two existing tuples. Essentially, what I am saying is, assuming I have these two tuples, A, B, C, A, B prime, C prime, in this relation, I need to imply I can swipe them that T3 and T4 will also be in this relation. If this holds for every single tuple that sharing the alpha value, it actually means condition on alpha, beta and gamma are independent with each other. Make sense? So that is intuitively what we are trying to model with this multivital dependency thing. Okay? So again, the definition might look really long, but essentially it doesn't tell you too much. All it's saying is if you have T1 and T2, you can swipe their beta and gamma, and you can still find those two tuples in the relation. Make sense? Any questions? Questions? Multivital dependency? Okay. So now let's look at this, right? So what multivital dependency do we have here? In this case, essentially, for every single person, right, if I have two tuples, right, for example, the first two tuples, if you swipe their language and program language, you get the third and the fourth tuple, right? So in this case, there's actually a multivital dependency from person to language, which means that condition person, language, and all the other tuples, which is programming language, which is left, are independent of each other. Okay? And then you also have personnel number, a multivital dependency from the person to the programming language. Okay? So these are the two multivital dependencies that you have in this schema. Similar to functional dependency, when you have multivital dependency in your relation, it could also cause a whole bunch of anomalies. And as we can see, it also causes essentially redundancy. So the way to think about multivital dependency, like intuitive way, is that if you have this multivital dependency from alpha to beta, then you can losslessly decompose this relation R. You can have one map the whole thing to alpha beta, you have another one, alpha and gamma, and you are able to join them together to make sure it's still lossless. Okay? So intuitively, this is what we are trying to model. So in fact, like the decomposition thing, like last time we defined it with a functional dependency, right? So actually, this is actually the tight way to model it, okay? So if you have the condition that we talked about last time, that there's a functional dependency from alpha to beta, alpha to gamma, then it's lossless. And if you have this multivital dependency between alpha to beta, alpha to gamma, right? So decomposition will also be lossless. Okay? So this is actually a tighter. So as we will see next week, it will be like essentially tighter to describe it, because whenever there's functional dependency, it implies you have multivital dependency. Okay? So this is actually give you kind of more instances that you can decide whether it's lossless or not. Okay, so this is about multivital dependency. So similar to functional dependency, if you still remember last lecture, you probably can reason about what we are going to talk about next time. That is, now we have this level of dependency, new notion of dependency. We need to think about how to reason about it. For functional dependency, that thing is Armstrong's axiom. For multivital dependency, we don't know. We need to talk about how to reason about multivital dependency. And similar to functional dependency, you have a whole bunch of normal forms, from the first to second to third to Bcnf. For multivital dependency, there will be another normal form that gets rid of multivital dependency, not functional dependency. And that is what we are going to talk about next week. So that's all for today. I'll see you guys next week.